Okay, so we're in our second week of business calculus, or calculus for social science and life sciences. We started looking at limits last week and looking at them geographically, so looking at a graph and finding where the limit was going to if it exists. Now we're going to look at limits algebraically. And so before we do that, I kind of wanted you guys to review a little bit from algebra. These are going to be tools that are going to help us. So problem 1 and problem 2. So it's going to be really helpful to be able to factor and then also to be able to rationalize a denominator. And so these are things that you should hopefully remember how to do. So take a moment and do the following problems, and then we'll talk about them. And while you guys are doing that, I'm just going to pause the recording. Okay, so you guys have had a moment to, or a little more than a moment, to work through or try to work through these problems as best as you could. And then you guys went into a breakout room and met with 2 other students and kind of talked about what you got. And I was able to get around to a couple of the breakout rooms and notice that some of you guys are still struggling with factoring. And that's kind of why I wanted to come in here and actually give these problems, because factoring, again, is going to be really helpful when we're doing limits algebraically. Okay, so when you are approaching factoring, the first thing you want to do is see if there's any greatest common factor. Is there anything in common with all those terms inside what you're trying to factor? So if I look at this, this has an x squared as one term, a negative 5x, and a positive 6. So I have 3 terms, and I noticed that there's not an x in all these 3 terms, and then my coefficients, there's nothing in common besides a 1 or a negative 1. So it's already, there's no greatest common factor with those. And so then I look at what type of, how many terms. That kind of clues me in how I'm going to factor. And I have 3 terms. It's a quadratic. I notice my coefficient in front of the x squared is 1. So that makes my life so much easier. So maybe recall, if you're factoring something in the form ax squared plus bx plus c, where a is equal to 1, so we could write it as x squared plus bx plus c. This is where you're looking for the 2 numbers that would multiply to give you your constant and would add to give you your coefficient in front of your x term, b. So let's say that you found that the 2 numbers, and they're arbitrarily, was e and d. So e times d would equal c, and e plus d would equal our constant b. If this is the case, then we can factor this as x plus e and x plus d. Okay, so let's look at that. So our example, our constant is 6. And so we're looking for 2 numbers that multiply to give you positive 6, but would add to give you negative 5. So I know some of you, oops, positive 6 and negative 5. I know some of you might do that x here, and you put your numbers here and you decide. I do kind of the same thing, it's just I just write it a little differently. But 2 numbers that multiply to give you a positive, and it adds to give you a negative. Well, remember, multiplying 2 negatives give us a positive. And I know I'm summing and getting a negative, so I know both of my numbers have to be negative. And so negative 5 times negative 1, that does multiply, sorry, negative 5 times negative 6 does multiply to positive 6, but negative 6 and negative 1. That multiplies to positive 6, but if we sum this, this is negative 7, so those aren't correct. So negative 2 times negative 3 is positive 6, and negative 2 plus negative 3 does give us positive 5. So this factors as x minus 2 all times x minus 3. And it doesn't matter which factor you had put first. So it could have been x minus 3 all times x minus 2. Okay, so the next example, trying to factor, again, you want to look to see if there's anything in common with all the terms. This one is called a binomial because there's only 2 terms. And 25 and the term negative 4x squared don't have anything in common. So if you have 2 terms, I look at it to see if I have a difference of squares. So is there anything that I could square to get the first term? Is there anything I can square to get that second term? If so, it's a difference of squares. And recall, if you have a difference of squares, there was a rule. So if we have a squared minus b squared, this factors as a minus b all times a plus b. And so looking at 25, think of what we can square to get 25, and let's think what we can square to get 4x squared. Well, we can square 5 to get 25, and we can square 2x. 2x times 2x is 4x squared. So we got it in this form, and so now we can say this is the same thing as our a value, which is 5. So 5 minus b, which is 2x, and 5 plus b, which is 2x. So if we distributed these and combine like terms, we would get our original. Okay, so the next example, factoring. I notice we have a trinomial, 3 terms. It's a quadratic, but unfortunately the number in front of the x squared is not 1. And so I have to use, and I use a trick that always works if it's factorable over the real numbers. And so some of you can do this by trial and error. Some of you, if you want to do it that way, I'm just going to go over what the AC method says. But basically, if you have something in the form of ax squared plus bx plus c, where a doesn't equal 1, we really have to put on a stipulation that a also doesn't equal 0, because if it's 0, it's not a quadratic anymore, it's a linear equation. So this is what you're going to do. You're going to look at what is the multiple of the coefficient in front of x squared a times your constant c. So you're going to figure out what that number is. So in our case, our a value is 3 and our c value is 4. If we multiply those together, 3 times 4 is 12. So kind of the same idea. We're trying to find 2 numbers that multiply to give us 12, but in this case, add to give us our b value. And if I look over here, my b value is negative 8. Okay, so what multiplies to 12, positive 12, and adds to a negative 8? So 12, 1 times 12, that's not going to work. 3 times 4, that would add to a 7 or a negative 7. 2 times 6. 2 times 6 is 12. 2 plus 6 is 8. But they both have to be negative?
Negative.
So negative 6 and negative 2. So let me know if you guys have questions. I'm just going to mute you, maybe. Okay. So this would have been 12, or multiplying 12, negative 8. And negative 6 plus negative 2 is negative 8. Okay, so this is where we have to do this trick. And what we're going to do is, instead of writing our middle term of negative 8x, we can rewrite that as a sum using those two coefficients we found. So we could technically rewrite this. Let's bring down our middle term, or first term, 3x squared. And let's rewrite negative 8x using these two numbers. So minus 6x, minus 2x. And then I'm going to bring down my constant plus 4. So a lot of times in math, we're just manipulating an expression or equation to get things to fall out like we want it to. And so we just manipulated this and rewrote negative 8x is the same thing as negative 6x minus 2x. So once you found those two numbers, rewrote your middle term with those two numbers, the trick is to factor by grouping. So one trick is when you're seeing 4 terms and you can't factor it, then to try this method, factoring by grouping. So you're looking at the first 2 terms and you're pulling out the greatest common factor of those 2 terms. So 3 and negative 6, the biggest number they both have in common would be a 3. And then x squared and x, what they both have in common is just a single x. And so if we pull out a 3x from the 3x squared, you'd be left with an x. If you pulled out a 3x from the negative 6x, you're left with a negative 2. So now let's look at those last 2 terms, and you want to pull out the greatest common factor. So it should give us the same thing inside the parenthesis when we pull out the greatest common factor. If it doesn't, then you probably pulled something out wrong and you want to look at it again. So looking at negative 2x plus 4, what they have in common, well, they both have a 2 in common. But I know if I pull out a positive 2, then I'd have a negative x left for the first piece, and I want a positive x. So instead of pulling out a positive 2, let's pull out a negative 2. So if we pull out a negative 2 from these 2 terms here, you're left with a positive x, and negative 2 times a negative 2 would give us that 4. And so now notice what's inside the parentheses is the exact same thing. So it's like we're pulling out the parentheses from both of those groupings. And so if you pull out the parentheses for that first piece, right, you would just be left with a 3x. And if I pulled out the x minus 2 from the second piece, I would be left with negative 2. And so this factors as, and it doesn't matter the order, but the factor of x minus 2 times the factor of 3x minus 2.
Hey, Professor, could you start up to the problem before, please?
Yes.
Thank you. Thank you.
Yeah, no worries. Any questions on this or factoring? So if this is something that, you know, yeah, it's starting to make sense, or I remember doing this, but I forgot, you might want to watch some videos, and they're great videos on just factoring. So go to YouTube and just type in, you know, factoring polynomials or factoring trinomials, quadratics. Also, you could watch if you wanted to. No, actually, I don't have that video. Sorry. Okay. Rationalizing the denominator. So sometimes it's really helpful to be able to multiply an expression by a fancy one to manipulate it to be easier. And so when it says rationalize the numerator, or it might say rationalize the denominator, you're trying to get rid of the radical in either that numerator or denominator. We are going to use that fact that I was talking about with the difference of 2 squares. So remember, if instead of going the opposite direction, if I had factoring it, but if I had a minus b times a plus b, recall this was the same thing if we FOILed this out and combined like terms, a squared minus b squared. if we square a square root, that radical goes away. But I can't just square a square, just square an expression. I could if there was an equation, but this is an expression. And so how we're going to manipulate this is that we're going to multiply this by the conjugate, which means the opposite sign in between the two terms. And that would then make us have a factor of a difference of squares if we had expanded it. So the conjugate of the numerator is 1 plus the square root of x. But in order to make this equivalent, I have to multiply by a 1. And so 1 plus square root of x all over 1 plus square root of x. Okay, so we can again distribute this and combine like terms, or we can go a shortcut and say, okay, well, I can just square my first term minus the square of my second term. And the square of my first term would be 1 squared minus the square of my second term, the square root of x squared. So it's easier, it's better if you actually don't distribute the piece that wasn't the conjugate, because that will help us later on. So this is the same thing as x minus 1 all times 1 plus the square root of x. So 1 squared is 1 minus the square root of x squared is just x all over x minus 1, 1 plus the square root of x. Okay, we're not quite done. I noticed that if you look at our numerator, 1 minus x, this right here, that binomial, almost looks identical to x minus 1. All they're off by is a negative sign. So if I pulled out a negative 1 from the numerator, so if I just factored out a negative 1 from the numerator, that would give me negative 1 plus x, but I'm going to rewrite negative 1 plus x as x minus 1, all over my denominator, which was x minus 1 in parentheses, and then times parentheses 1 plus square root of x. And so notice that we have common factors that we can simplify, x minus 1. And so this would leave us with the numerator of negative 1 all over 1 plus square root of x. So if you have two terms, and one of them has a radical, either in the numerator or denominator, sometimes that's helpful if we multiply by that conjugate, and multiplying by a fancy one using that conjugate in the numerator denominator. Okay. And the last problem, that was just kind of a review from last week, but with some context as an application. And so consumer demand. So the following says, when a price of an essential commodity, such as gasoline, rises rapidly, consumption drops slowly at first. If the price continues to rise, however, a tipping point may be reached, at which the consumption takes a sudden, substantial drop. Suppose the company graph shows the consumption of gasoline, capital G of T, in millions of gallons in a certain area. We assume that the prices is rising rapidly. Here, T is representing our months. And again, G of T, that's representing the gallons. And where did it say millions? Yeah, millions. Okay. T is in months after the price began to rise. Use the graph to find the following. So we're looking at the limit as T approaches 12. So what's happening as we come in on the left and the right of T equals 12? Is that going to the same exact Y value or getting really, really close to that same exact Y value? Which we can see that it is. And that Y value that we get back is 3. Okay. And this is in terms of millions. So 3 million. So what's happening as limit as T approaches 16 of G of T? Well, if we look at that, there's a jump in my graph at 16. I notice that on the left-hand side, so the limit as T approaches 16 on the left, a capital G of T, this one would be equal to my value of 2. And if I look at the limit as I'm pushing it on the right, oops, sorry. We equal, coming in on the right, we're getting to 1.5. If our limits are not the same on the left and the right, then the limit doesn't exist. And it's not x, it's t. So the limit as t approaches 16 does not exist. Okay, so part C wants to know what is g of 16? So what is that point on the graph? When t is 16, what is that y value, g of t? Well, looking at the graph, you want to see is there a solid point? You're looking for the solid point at 16. And so there is a solid point right here. This one's an open circle, meaning it gets close, but it never equals that value. So g of 16, this is equal to our y value of 2. And then the tipping point. So if you go back, it says, if the price continues to rise, however, a tipping point may be reached, which the consumption takes a sudden substantial drop. So notice at t equals 16, there's a substantial drop in here from $2 to $1.5. And so our tipping point we can see is t equals 16. Let me pause. Okay, so hopefully with a review of some factoring and how to rationalize the denominator, that was kind of good. And this will help you when we're looking at solving, looking at limits algebraically. So these rules, we looked at these last week. I just kind of wanted to put them up there again. So if we take a limit as x approaches a value of a constant, you always get that constant back. These rules help us. We really don't usually use these rules, but with these rules, basically we can just go in and plug in our value that x is approaching into our function, and we might get spit back a result by using those rules. So let's look at maybe the following 31. So here I'm looking at the limit as x is approaching 3 of x squared minus 9 all over x minus 3. Okay, so with the limit rules, and I'm going to just write these limit rules again real quick. I can take the limit of my numerator all over the limit of my denominator. And then basically I can take the limit of my first term minus the limit of my second term. I'm really just going in here again, and wherever I see an x, I'm replacing it to what we're getting close to on the left and right, which in our case is 3. So if we go back in here and wherever we see an x, we put a parentheses. And we go back in and plug in a 3 wherever we saw our parentheses. So if we do this, 3 squared minus 9, well, that's 9 minus 9, all over 3 minus 3, which is 0. And 9 minus 9 is 0. So we have 0 over 0. If we just got 0 in the denominator, we would say it's undefined. If we just got 0 in the numerator, then that would equal 0. But if you get something in the form of 0 over 0, this is called an indeterminate form, which means it doesn't tell us anything about that limit, and you need to go back to that, what you're taking the limit of, and you need to manipulate it so that you don't get this form 0 over 0. And so some ways that you can manipulate it is by factoring the numerator and denominator and canceling like factors, or if I had radicals, maybe trying to rationalize and get rid of the radical. So let me just again write down what I had said here. So note 0 over 0 is called an indeterminate This doesn't tell us anything about the limit. So you got to go back and manipulate. So you need to go back and manipulate the function. So the limit gives us a value. Okay, so like I said, we can factor. If you notice that numerator x squared minus 9, that is a difference of 2 squares. And so x squared minus 9 that factors as x minus 3, x plus 3, all over our denominator of x minus 3. So factors of x minus 3 cancel both in the numerator and denominator. And so now we're looking at the limit as x is approaching, -1. Sorry, x is approaching 3. So we're looking at the limit as x approaches 3 of x plus 3. So if we go back in here and wherever we see an x, we plug in 3. Notice when we plug it in now, we get back 3 plus 3, which is equal to 6. Okay, so the limit of x squared minus 9 all over x minus 3 as x approaches 3 gives us a value of 6. So it's actually undefined there at x equals 3, but we're getting closer and closer to the y value of 6 there. Okay, let me pull a different one. How about 38? And I'm going to need a lot more room. Okay, so we're looking at the limit as, what did I say? Did I say 36? It doesn't really matter. 36, I think is way too easy. Let's do 38. So limit as x is approaching 0 of -1 all over parentheses x plus 2 plus 1/2. And that is the numerator, and that's all over x. So notice when you go back in here and wherever you see an x, you go and you plug in 0. And it's not going to do it. So let's go back in and plug in 0. We get -1 all over, I see an x here, so I have 0 and then plus 2, plus 1/2 all over my denominator, which was 0, or x, which I'm plugging in 0. And so if I do this, I get -1/2 plus 1/2 in my numerator, which is 0 all over 0. And so we need to go back and we need to manipulate that expression so that when we do take the limit, we get a value that's not an indeterminate form. Okay, so I noticed that what we're taking the limit of is a complex fraction. And so maybe we can manipulate this so that it's not a complex fraction anymore. So complex fraction, you have fractions within fractions. There's two kind of ways that you can deal with that. I prefer to multiply by my fancy 1, so that would get rid of my fractions. And so if you look at the fractions within the main fraction, so there's just 2 fractions within this main fraction, you want to find the LCD. So you want to find the least common denominator of x plus 2 and 2. So our LCD is the factor x plus 2 all times the factor just 2. So we're going to go in here and we're going to multiply this by a fancy 1. So x plus 2 all times 2. And x plus 2 all times 2. If it helps you to see it, this is the same thing as we could write this in the numerator as a fraction as over 1. And so when we distribute, you have to distribute to each term in our numerator, our denominators are going to cancel, and we're not going to have a fraction anymore. in that numerator. So we have the limit as x is approaching 0. And so I have -1 all over x plus 2 times my LCD x plus 2 times 2 plus this 1/2 all times my LCD x plus 2 all times 2 all over my denominator, which was x, times my LCD x plus 2 times 2. So we did this so things would go away. Those x plus 2's cancel, and all you're left with is that -1. So the limit as x is approaching 0 of this -1 here times this 2 here. So -1 times 2, that gives me -2. Plus, notice here, my 2's cancel, and I'm left with x plus 2. So I'm just going to write it as x plus 2. Don't expand out the piece in the denominator. If we do that, we're going to have to go back and we're going to have to factor it. So now notice my numerator, I have a -2 plus x plus 2. So I have like terms, I can cancel out the -2 plus 2. That would just leave me an x in my numerator. All over this x, all times x plus 2 times 2. So if you don't see that there's a common factor of x there, you'll notice when you plug in 0 for x, you still get 0 over 0. So let's cancel those x's. And so now we're really just looking at the limit as x approaches 0 of 1 all over 2 times x plus 2. I can have that 2 in the back like I've had. Now if you go plug in 0 wherever you see an x, so you have 1 all over 2 all times 0 plus 2, or 1 over 2 times 2, which is 1/4. Okay, so we found the limit of that value to be 1/4. Okay, so this is probably a good spot to take a break. Let me pause the recording. Okay, so we're looking at limits algebraically, and now let's look at limits and a rule of what's going on when we're going to infinity or negative infinity. Before we look at this limits to infinity, let's look at what's happening graphically. So basically, there's multiple things that could happen. And so let's say we have some graph f of x. And let's say it looks something like this. Okay, so we have something that looks like this, and we're looking at the limit as x is approaching infinity. And so what we're looking at is what's happening to our y value as x goes to positive infinity. So if we follow the graph, as x is going to positive infinity, do we reach or come to or get very close to one particular number here? And we don't. And so it doesn't exist, but notice it is going and shooting upwards to positive infinity. So even though it doesn't exist, we'll write down that it's going to either positive or negative infinity, if that's the case. So let's look at the limit going in the opposite direction as x is approaching negative infinity. So as x goes to negative infinity, is there some value you're getting closer and closer to, or even hitting, as we go to negative infinity? So notice there's actually this horizontal asymptote here, And so the graph as x is going to negative infinity, our y value that we're getting is -1. So the limit actually exists as x goes to negative infinity, and it's equal to, in this case, -1. Okay, so let's look at this limit, limits to infinity. And so if you have 1 over some variable, x raised to some power, then that's going to be going to 0. Let's pull up Desmos. So we can just look at graphs. Okay, so let's look at what happens to functions 1 over x, 1 over x squared, 1 over x cubed, and see if we can see what's going on with all of those. So if I looked at the graph of 1 divided by x squared, so notice here you have the shape, and as x is going to negative infinity, if we follow this along, notice that y value is getting closer and closer to 0. Same idea on the right-hand portion, or the end behaviors of the graph as x goes to positive infinity. Notice that y value that you're hitting, you're getting closer and closer to 0. It actually is undefined at x equals 0 because that sets our denominator equal to 0. But the graph is approaching 0 as x goes to infinity. So let's look at the same thing, but this time let's look at it with an x squared in the denominator. Where's my caret? So same idea, notice as x goes to negative infinity, we're getting closer and closer to 0. As we're going to positive infinity, we're getting closer and closer to 0. So any power I put up here, notice that that's always going to be the case. Left and right end behaviors of our graph always goes to 0. It really doesn't matter what number I have up here. So let's say I have 5. That constant's not going to really affect it. Or even if I have a -1, it's going to affect the graph, but it's not going to affect the end behaviors of the graph. It's always going to be going to 0. Which makes sense. If you think about it, as x is going to infinity, doesn't matter if you're raising it to a power or not. If you are, it's just going to infinity faster. But some small number over a huge number, like 1 over 10 is 1/10. 1 over 100 is 1/100th. 1 over 1,000 is 1,000th. And so every time I make that number bigger, of the power of 10 in the denominator, that number is actually getting smaller and smaller, going to 0. So that's that idea behind what we were just looking at with this limit law. So it says for any positive real number n, if we look at the limit as x is approaching infinity of 1 over x to the nth, we get 0. And same sort of idea, if we look at the limit as x approaches negative infinity of 1 over x to the n, we also get back 0. Okay, so I'm going to pull an example. So how about the limit as x is approaching infinity of 3x all over 7x minus 1. So limit as x is approaching infinity of 3x all over 7x minus 1. So if you go in here and you plug in infinity wherever you see an x, you have your numerator, which is blowing up, because 3 times something getting large is getting really large. And we have our denominator blowing up. And so actually, when we go back in there and plug in infinity, you should see that you get kind of like infinity over infinity. So this is another indeterminate form. Just like 0 over 0 is an indeterminate form, that limit didn't tell us anything, and so we had to go back in there and we need to manipulate this so that when we do plug in infinity, it goes to 1 value. And so the trick for these is if it's going to be infinity over infinity, what you want to do is you want to look at the degree of the numerator. So that is the variable to the highest power. So that would be x to the first. The degree of the denominator, so the highest power of x is x to the first. And if we multiply by 1 over that variable to the highest power to the numerator and denominator, then it will fall out that we don't get infinity over infinity. So let's just look at that. So I'm going to take this 3x all over 7x minus 1. And I'm going to multiply this by a fancy one. And my fancy one is going to be 1 over x. All over 1 over x. So we need to take this 1 over x and distribute it. Well, we only have 1 term in the numerator, but we have 2 terms in the denominator. So bring down our limit until you actually take the limit, unless you do the work on this side. But we're looking at the limit now. As x approaches infinity, well, 3x all times 1 over x. The x's cancel, and you're left with 3 times 1, which is just 3. If I distribute 1 over x times 7x, well, 7x times 1 over x, the x's cancel, and you're left with 1 times 7, which is 7. And then minus 1 times 1 over x is just 1 over x. So using our limit laws, we're looking at the limit of our numerator, which is a constant. A limit of a constant is just that constant itself, which is 3, all over the limit of our denominator, which we could break up into pieces, a limit of 7. Limit of a constant is just 7, minus, well, if you put infinity in there for x, 1 over infinity, this value right there is getting closer and closer to 0. 1 over infinity goes to 0. So I can say this is really 7 minus 0, which is equal to 3/7. So if we go back and we look at what this graph looks like in Desmos, we'll see that there's a horizontal asymptote. As x is going to infinity, that y value is getting closer and closer to 3/7. See if I can pull that up. So let me just graph that real quick. So we had 3x divided by 7x minus 1. Okay, so as x is going to infinity, so I can plug in points right here. I get 0.447 as I get way out here, still getting closer and closer. Looks like a horizontal line. 0.43, 0.432. So notice as I go further, it's getting closer. It's saying the same number, 0.432. And so I can see that's going to 0.431. Oops, now we're going to 0.431. But if you look at, what was our number? 3 over 7. 7 goes into 3. Well, it doesn't. Add a 0. 7 goes into 30 4 times, so 0.4 something. So we were able to do that without having to go through and graphing this. Okay. I saw one that could look good too. So we didn't try one yet where we rationalize the denominator or numerator. So let's look at a different limit. Let's look at the limit as x approaches 36. And we have our numerator as square root of x minus 6 all over our denominator, which is x minus 36. So if you go in here, wherever you see an x, if you go back and you replace x with 36, notice that you get square root of 36 minus 6. Well, square root of 36 is 6. 6 minus 6 gets us 0. All over 36 minus 36, which is 0. So indeterminate form. And so we want to manipulate it so that when we take the limit, we do get a value. So if you can factor, you would try factoring. I notice I have a radical in here, so we can use what we did in the warm-up earlier today. So if we rationalize this numerator and we multiply this by a fancy one, which would be the conjugate of whatever square root of x minus 6 is. So the conjugate is square root of x plus 6. Square root of x plus 6. So I'm going to use the rule. This is a difference of squares. So if I just square my square root of x minus, and I just square my 6 all over my denominator, and I'm just going to leave it in factored form, x minus 36, that quantity all times the quantity square root of x plus 6. So squaring square root of x, I get x, minus squaring 6, I get 36, all over x minus 36, x plus, or square root of x plus 6. So again, if I go back in here and plug in 36 for x, I get 0 over 0. But notice that we have a factor of x minus 36, both in the numerator and denominator. So if those go away, you're really just looking at the limit as x approaches 36 of 1 all over the square root of x plus 6. So 1 all over, so wherever you see an x, replace it with 36. So 1 all over the square root of 36 plus 6. So 1 over 6 plus 6, which is 1/12. Okay. So the examples I pulled from the book that are below are more to, some of them are to infinity. So let's look at another one to infinity and use the trick I was telling you about before. So if we had, let's say, x to the 4th minus x cubed minus 3x, and that's in our numerator, divided by 7x squared plus 9. So if we went in there, we plugged in infinity wherever we got an x, Well, the numerator is going to blow up. That x to the fourth is pretty big. It's going to go faster than x cubed or minus 3x. And the denominator is going to blow up. They're both going to go to a positive infinity. So indeterminate. So you want to look at the variable to the highest power in the numerator. And if I did that, that would be this x to the fourth term. And look at it in the denominator, which in this case would be the 7x squared, or just x squared. So the largest degree will be the x to the fourth term. And so we want to multiply this by a fancy one, and that fancy one is going to be 1 over x to the fourth, all over 1 over x to the fourth. Okay, the limit as x approaches infinity of this x to the fourth minus x cubed minus 3x all over 7x squared plus 9. So if we distributed, we get the limit as x goes to infinity. Well, this is going to give me x to the fourth over x to the fourth when I distribute, minus x cubed all over x to the fourth, minus 3x all over x to the fourth, all over, so distributing in the denominator, we get 7x squared all over x to the fourth, plus 9 all over x to the fourth. You're using rules of exponents. Remember, if you are dividing, you have the same base. So b to the m divided by b to the n. Remember, the rule of exponents was subtract them. So this would be b to the m minus n power. So I'm using this case here. So 4 minus 4 is x to the 0 power, or anything raised to the 0 power other than 0 is 1. Or you can just simplify and see that's 1. So you got the limit as x goes to infinity of 1 minus, so x cubed over x to the fourth. So this is 3 minus 4, which is a negative 1. So that would actually be in the denominator, 1 over x minus, so this gives me 3 all over x cubed, all divided by, well, 7x squared over x to the fourth is 7 divided by x squared, plus 9 over x to the fourth. So we're going to use the fact that if you have the limit as x is approaching infinity of 1 over x to the n, this goes to 0. So notice as we put in infinity, wherever we saw an x, this piece would go to 0. This piece would go to 0. Uh-oh. I think we're going to have a problem. This value is going to go to 0. This value is going to go to 0. So 1 over 0, though, that's undefined. If you look at this and we go to the graph, what's going to be happening is instead of going to one particular y value, the denominator or the numerator has a higher degree, so it's blowing up faster. So what's happening is it's going to be shooting off to positive infinity. So let's just look at that graph real quick. I need to write down the formula or I won't remember our function. Okay, so looking at the graph, I'm going to go in here, rewrite it. So numerator, we had we just had x to the fourth minus x cubed minus 3x, all divided by 7x squared. Oops, I didn't mean to do that. Darn it. Let's try to. All divided by, sorry about that, 7x squared plus 9. I guess in looking at our graph, actually looks like a parabola shape. And notice that in behavior there, as x is going to infinity, your x value is getting larger and larger and larger, your y values are blowing up and going to positive infinity. So it doesn't exist. Okay, so we still haven't finished 3.1. I still want to go over a couple more types of limits that you're going to see in this section, which is looking at piecewise functions. So we'll finish up 3.1 on Wednesday, and we'll also start getting into 3.2, which is continuity, in which we've kind of done a lot of that so far when we were looking at limits graphically. But this is a good spot to stop right now. So let me stop the recording and then I'll take any questions if you have any questions.